So this is starting chapter 16 notes on acid base. For these notes, I suggest you have some kind of highlighter available because I've given you a lot of background information, and I just want to make sure that you focus on the definitions and the other things that I wrote down, what you need to remember. So we have what we call three different theories or three different definitions of how we define acids and bases. So the first one is called Arrhenius, and this is the one you probably remember from first year chemistry and probably going to be the one that you remember even after this class. And that is acids produce hydrogen ions in aqueous solutions and bases produce hydroxide ion in aqueous solutions. So please be sure that in your definitions, you understand that this is only in aqueous solutions, and that needs to be included in the definition. So you can't just say acids are H+, bases are OH. So examples of Arrhenius would be anything listed with an H first. So again, you could take any of your strong acids, any of those H listed first is considered an Arrhenius acid. And then anything with an OH, whether it be one OH or two OHs like magnesium hydroxide, that's considered to be an Arrhenius base. So the one that we're going to spend the most time on in this discussion is going to be what we call Bronsted-Lowry definition. And it includes more acids and bases than just a typical Arrhenius definition. So that's why we have the theories that we do, is to include more and more things that have acidic and basic properties. So acids, please know they are hydrogen ion donors, okay? And then H+ acceptors are going to be bases. So when we are looking at Bronsted-Lowry acid-base discussion, you kind of need an equation to figure out who is donating and who is accepting. So what you're going to see is these are going to be what we call equilibrium situations. And so when we're looking at Bronsted-Lowry, we are always going to be defining them in conjugate acid-base pairs. Okay, so conjugate base pairs is going to be what we describe. So when we are looking at HF, okay, HF in an aqueous system is going to produce H3O+ and F- fluoride. Well, H3O+ is called hydronium ion. You are going to have to be familiar with some of these words because sometimes in discussions, instead of writing the formula, you might see the words. So HF is becoming F-, okay, and H2O is becoming hydronium ion. So the HF is becoming F-. You could see that it's essentially donating an H. So that's acting like an acid. So I'm going to write an A underneath for acid. Then on the reactant side, whatever is acting like an acid, the other one has to be acting like a base. And we could tell it's acting like a base because it's becoming hydronium ion. So it's accepting an H+ to become hydronium ion. Now, over on the product side, we're going to call these conjugates. Now, we will discuss a little bit further on in the lecture, how do we tell whether or not something is the conjugate of the other. It has to do with strength, and we'll talk about that later. But for right now, we're going to say acids and bases are on the left, conjugates are on the right. Well, F- does not have any H on it, okay? And that's always going to be my go-to question whenever you ask this. So there's no way you could act like an acid because there's no H to donate. So this has to be acting like a conjugate base. Please note that any acid always becomes the conjugate base and vice versa. So the base becomes the conjugate acid. Does this H3O+ have an extra H to donate, an H+? Sure. Okay, so that's going to be your conjugate acid. So HF and F- are your conjugate acid-base pairs. Water and hydronium ion are your conjugate acid-base pairs there. Okay, so the second example I have on your notes is ammonia. Okay, so this is ammonia. Okay, and NH4+ is ammonium. And these two always get confused in this particular chapter. So that's why you need to pay attention to that. So ammonia is becoming ammonium and water is becoming hydroxide ion, okay? So the ammonia is essentially taking on an H plus. So since it is taking on an H plus, this must be acting like a base. And you need to also know ammonia is considered a base. So water in this case is acting like an acid. Interesting, because in the last example it's acting like a base. We'll come back to that as well. So NH4 plus and OH minus. Okay, OH minus has lost its H. So this has to be acting like the conjugate base. Or you need to focus on NH4 plus. I got an extra plus there. That's my conjugate acid. Now, it doesn't always work this way, but typically the minus is going to be your conjugate base, the plus is going to be your conjugate acid, but that's not always the case, so keep that in mind. So I'm going to pause the video, see if you could do the next example, finish the two products, and then label it. So it becomes acetate ion and hydronium ion. Acetic acid, that's the first one, is acting like an acid. This is acting like a base. You produce acetate ion, again, some words that you need to be familiar with. And then the hydronium ion, these are the conjugate base, that's your conjugate acid. It doesn't matter which way you write these as products, by the way. All right, so the last definition we're going to talk about is something called Lewis, okay? And this is electron pair acceptor for an acid and electron pair donor for bases. This includes pretty much all acids and bases, so that is why it's a very useful definition compared to the other ones. The good example I'm going to use with this is going to be our friend ammonia. And ammonia is unique because it has a lone pair on it, okay? The nitrogen does. So when it reacts with an acid, something with an H plus, it becomes our friend ammonium ion, okay? So what has happened is I've essentially made a bond there with the two electrons from the nitrogen. So the nitrogen, again, is donating the electron pair. So it's acting like a base, and then whatever acid you have with it is going to essentially go where that lone pair is and then make a ion from there, because this, again, is going to be our ammonium ion. Now, good news is you don't need to know Lewis definition for the AP test, and I'm not expecting you to know it as well. I like to introduce it just because if you see it in the book, you know what it means. This is much more applicable to what we call organic chemistry. So that's why they kind of taken it off the test. And I'm not going to ask you about it either, but I still like to introduce it to you. All right, so the last thing I want to talk about in this video is in relation to like Bronson-Lowry acid-base pairs, is what we call metals with high oxidation states. So these are going to be metals that have a +3 or +4 charge on them, oxidation state. So what we have is something called hydrolysis, and we're going to see this in a lab we're going to do and some other discussions. Please note that they always form what we call acidic solutions, but their equations look a little different, so that's why I kind of need to go over it with you, because we're going to see it in a couple different places. So the example that I've given you in your notes is aluminum has a +3 charge. What it does is make what we call a complex ion with water. Again, you don't need to know complex ions in respect to how they form, but it does form with 6 waters, and you still have the +3 on the outside. Well, once it's in that aqueous environment and this complex ion has formed, what happens is, and I know it's bizarre, is one more water causes it to be acidic, because what it produces is the hydronium ion, and the hydronium ion makes something acidic, okay? Anytime you have an H plus or hydronium ion. But what you will see over here is you've essentially converted one of those waters into an OH minus, and so that's why you end up with AlH2O5 OH2 plus, because that OH has that negative charge. So this is acting like an acid. The water is acting like a base. And of course, my hydronium ion will always be considered a conjugate acid, and this is going to be your conjugate base. So this is going to be a pretty similar equation you're going to see with multiple metals. So I would like you to try Fe. See if you could write the second equation where you have one more water added on and it shows you your conjugate acid-base pairs. So pause the video and see if you could write it. All right, so you're going to take this complex ion here and you're going to add another water to it. You're going to make hydronium ion, and then you're going to have Fe with 5 waters, an OH, and a 2+. Again, this will be your conjugate acid. This will be your conjugate base. So again, anytime you see any metals with water, you're going to have an acidic solution. So we'll come back to that a little bit later on.